discrete whole life annuities. Now we are going to look at the discrete whole life annuities. Let's assume that the payment of the annuities will be $1 every year. So it will be paid discretely. Now let's look at the annuity due first, where the payment will be made at the beginning of the year. So let's say you have a payment of $1, $1, $1, $1. It will keep on continuing $1 up until when the persons die. Let's say he dies somewhere here, future lifetime up until here. Here no more payment anymore, but then he leave a more than kx but lesser than kx plus 1. So if you look at this type of the annuity, it will be y, the presence value of the random variable, equals to a double dot. Usually it will be up until tx, but now anything that's happening in between kx and kx plus 1, it will be up until kx only. The amount of the payment will be collected. So for here it will be kx plus 1. So you can rewrite it as 1 minus v kx plus 1 over d for any kx equals to 0, 1, 2, 3 and so on. Here has to be kx plus 1 because we didn't really know whether it is here, the persons die, since we only collected up until kx. If it is, let's say, kx plus 2 here, the persons die somewhere here, here would be kx plus 2. See, it's continue. Okay, so what would be the presence value of this actual presence value of this random variable? We can use the similar approach for the continuous case. Here it will be equals to 1 minus ax over d. And then if you were to look at the variance for this case, it's gonna be variance of this y which will be equals to 1 over d square times with 2ax minus ax. Variance of a constant is 0. Okay, this one you can factor out, 1 over d square variance of v kx plus 1, which is also equals to 2ax minus ax square. Another way of determining the expected present value of this case is, let's look at this timeline again. 1, 2, 3, it will continue forever. Payment is $1, $1, $1, $1, and so on. Okay, so this is the amount of the payment. And then the discount factor, for this case it will be 1 because you don't have to discount anything. Here is v square, v cube, and then the probability of this payment will be made is 1 because it is at the start of the policy. Probability of this payment would be made is px because he has to survive from here to here to make this payment, and probability of this payment will be made would be 2px. He has to survive these 2 years to make this payment, and it will continue like that. So expected value of this would be 1 plus v px plus v square to px plus and so on. So if we want to rewrite it in a simple term, we can say that this is equals to summations from k equals to 0 up until infinity v to the power of k px. Okay, this is for the annuity due. When we are looking at the annuity immediate, let's change the pen color first to differentiate the annuity due and the annuity immediate. So if we look at the annuity immediate, the start of the payment will be here, here, here. It will continue forever. So the difference between the annuity due and the annuity immediate is only this payment. For annuity due just now, we have actual notations for annuity due, which is a double dot x. Okay. Now, when we are looking at the annuity immediate, it will be ax, which is equals to whatever that a double dot x is, minusing the first part. So you are going to get this one equals to a double dot x minusing 1, because that's the only difference between the immediate and the payment of the annuity due. Only this part that will not be included in the annuity immediate. That's it for the whole life for annuities for the discrete case. Thank you.